All right, so welcome back to day 14. Today is the final day of week number 2. So today we're looking at the final 2 lessons of the intermediate machine learning course on Kaggle. Lesson number 6, which is called XGBoost, also known as extreme gradient boosting. We're also going to look at lesson 7, where we are introduced to the concept of data leakage. So without further ado, let's have a look at lesson number 6, XGBoost. All right, cool. So here we have a brief introduction of what gradient boosting is. So to save you some time, gradient boosting is an example of an ensemble method. So similar to the random forest model we saw in our previous course, in the introduction to a machine learning course, where random forest is an ensemble method, gradient boosting is another example of an ensemble method. And I've written an article before, and in the article I go into detail the similarities and the differences between these two ensemble methods, between random forest and gradient boosting. I'll put a link in the video description, so if you're interested to learn more on this topic, feel free to have a look just have a look at the article, and hopefully you gain some value out of that. So in random forest, we're using multiple independent decision trees in parallel, meaning we build multiple decision trees, and each decision tree will produce a prediction result. And what random forest does is it'll take the average, or it'll aggregate those results and give a final result. And how gradient boosting is different from random forest is that instead of the trees being parallel or being independent, gradient boosting iteratively improves upon the previous tree. Meaning gradient boosting will start with a simple tree, and then it'll build a next tree that builds upon the first one, and then you'll build another one that builds upon the previous one, and so on and so forth. The idea here is that the subsequent trees will try to minimize the error that the previous tree has made. So next time when you see random forest, think about parallel and independent decision trees. Next time you think about gradient boosting, think about sequential iterative trees. Yeah, so I hope that clears up the differences between the two ensemble methods, but essentially in a big picture overview, they both serve the same purpose of minimizing underfitting and overfitting. So in random forest, we saw how different decision trees can minimize overfitting because we're spreading the risk of overfitting across multiple trees rather than just relying on one. Gradient boosting is exactly the same. So by building sequential trees, each sequential tree will improve upon the result from the previous tree, and as a result give us a much better prediction accuracy than if we had just have one single tree by itself. Cool. So here they go into detail how the algorithm works. So first we use the current ensemble to generate predictions for each observation in the dataset. These predictions are used to then calculate a loss function, and then we want to use the loss function to fit a new model, which will be added to the overall ensemble method. And then finally, we want to continue to add new models to the ensemble, and then repeat the whole process until we get a final prediction. So this is a diagram of what's going on. So we have a naive model, so a simple model to just to help us kickstart the model. We want to make predictions. We want to calculate the loss. We want to use that loss to train a new model, add that new model to the ensemble, make predictions, calculate loss, and so on and so forth. So this process will keep repeating itself until we get a final prediction. So essentially, this is how gradient boosting works. So let's now look at an example in practice. I'm just going to skip all this because this cell here just pretty much just helps us get set up with the training and validation data. All right, so here we're importing XGB regressor, which is the extreme gradient boosting algorithm. And then we want to fit it to the training data. And then here we want to calculate the mean absolute error between the model predictions as well as the target in our test set. And so the mean absolute error is 238,794. Cool. So the next section that we're going to look at is called parameter tuning. So XGBoost is similar to other models in machine learning. They have hyperparameters, and these hyperparameters will dictate how the model behave, the overall structure of the model. And so here we're going to look at a few parameters within the XGBoost model itself. The first one is called N estimators. So N estimators specify how many times we're going through the modeling cycle. So if we scroll up and have a look at our diagram again, so N estimators will inform the model of how many times we want to repeat the whole process. So one process is consists of a new model being added to our overall ensemble. So n estimators tells the gradient boosting model how many times we want to go through this particular cycle. So the more estimators we add to our gradient boosting, the more overfitting it is, because we are getting very fine into the small detail, into the small error that we're trying to minimize it. Sometimes they'll cause overfitting, which is not good, but we also don't want to have too little estimators, which can cause underfitting. We're told that if n estimators is set too low, this will cause underfitting, which leads to inaccurate predictions on both the training data as well as the test data. Too high of a value for n estimators will cause overfitting, which causes accurate predictions on the training data, but inaccurate predictions on the test data, because the model fails to generalize on the data that it has not seen before. It fits very well to the training data, the data that we use to fit the model, to train the model. The model gets very good and accustomed to that particular data set. But when it comes to the real world, on data set that the model has not seen before, it is unable to replicate that level of accuracy. Cool. Another parameter is called the learning rate. So think of learning rate as the weight that we're putting on each of the trees. So as I mentioned earlier on, that gradient boosting involves multiple sequential trees. So learning rate will dictate how much weight is being put on each sequential tree when we're making a final prediction. So for gradient boosting model, we usually try to set our learning rate a little bit lower, because we want to take into account multiple sequential trees. We don't want a single decision tree to take up the majority of a prediction. We want to spread it out across multiple sequential trees. Cool. So here we are instantiating a model to have 500 estimators. We want to proceed to feed that training model and then use that model to make predictions, pretty much. All right, cool. So the next hyperparameter that we're looking at is called early stopping rounds. So this particular parameter offers a way to automatically find the ideal value for n estimators. Yes, so early stopping rounds causes the model to stop iterating when the validation score stops improving. So usually we set a high value for n estimators, and then we use early stopping rounds to find the optimal time to stop looping through or iterating. Let's move on. Yes, so learning rate, we briefly spoke about this early on. So instead of getting predictions by simply adding up the predictions from each component model, we can multiply the predictions from each model by a small number before adding them in. So this small number is known as the learning rate, or if you can think of it as weight. So we're taking sort of the weighted average of the sequential trees, and the parameter that dictates those weights are called the learning rate. In general, this is going back to the point I spoke about just then, a couple of minutes ago. In general, a small learning rate and a large number of estimators will yield more accurate results, especially for gradient boosting model. So as a default, XGBoost sets the learning rate to be 0.1. Yeah, so feel free, you can obviously change this up or use Greatshirt CV to help you find the most optimal hyperparameter. Cool. So here we're looking at instantiating a model with those parameters. Next one is called n jobs. So on larger data sets where runtime is a consideration, you can use parallelism to build your models faster. It's common to set the hyperparameter n jobs equal to the number of cores on your machine. So n jobs is essentially just to make sure that your model doesn't take too long when you're running the model, because gradient boosts usually take quite a long while, especially when it's training. And yeah, n jobs will help with your runtime essentially. So to summarize, XGBoost is a leading software library for working with standard tabular data, so with rows and columns, as opposed to more exotic types of data like images and videos. Cool. With that in mind, let's begin the exercise and see how we can apply the model in practice. All right, cool. The notebook's ready. Let me just go ahead and run our first cell to setup. All right, setup is complete. This next cell is essentially just preparing our training set and our validation set. I think that's ready. All right, let's move on to step number one. So step number one is building out our model. Begin by setting my model number one to an XGBoost model using the XGB regressor class. and then we want to set a random seed. So random state is a parameter that allows for model reproducibility. So I spoke about this a couple of videos before. The whole point about setting a random state is because we want to be able to reproduce a particular result. And so by setting a random state, we can be sure that we can recreate the same result if we call on the same random state again in the future. All right, cool. So we're starting off nice and simple. We need to instantiate our model. So let's just call XGB regressor. And then we want to set the random state to 0. And then we want to go ahead and fit the model. So my model 1 dot fit x train and y train. So let me just go ahead and run the cell. Beautiful. So part B, set predictions 1 to the model's predictions for the validation data. Recall that the validation features are stored in xValid. All right, cool. It's pretty simple. Now that we've defined our model, we've fit our model to the training data. Now we want to make predictions on xValid. So let's call on our model called my model 1 dot predict. We want to pass in xValid. Beautiful. So part C, finally use mean absolute error to calculate the mean absolute error corresponding to the predictions for the validation set. Recall that the labels for the validation data are stored in yValid. Cool. So we want to calculate the mean absolute error between our model predictions as well as yValid. So our predictions is called prediction 1, and we also want to pass in yValid so that it can calculate the mean absolute error between those two variables. Let's run that cell. So the mean absolute error is 17,662. Cool. Let's see if we can improve upon this result looking at step number 2, by setting my model 2, so this is our second model, to an XGBoost model using XGB regressor. Figure out how to change the default parameters like n-estimators and learning rate to get better results. Fit the model, set predictions to model predictions, and then calculate the mean absolute error. In order for this step to be marked correct, your model should attain a lower MAE than your first model. Cool. So let's just go ahead and do these 2 steps first because these 2 steps are pretty identical. So my model 2 dot fit x train and y train. As for predictions, we want my model 2 dot predict, and then we want to pass in xValid, and then we want to calculate the mean absolute error. So mean absolute error, we want to pass in our predictions, so predictions 2 as well as yValid. We need to uncomment this in order to print out the mean absolute error. All right, so cool. So now we need to alter our n-estimators as well as our learning rate to see if we can get a better result than our first model, than our previous model. So XGB regressor. So we want to set an estimator to be something. We want to set the learning rate to be something, and then we want to set a random state equal to 0. All right, let's think about n-estimators. So what is the n-estimator for our previous model? So in the previous model, we just used the default because we didn't specify anything, so it will just use the default. So let us have a look at what the default is. So what we can do is we can do print XGB regressor to see what the default parameters are and see if we can use different values for those parameters and see if we can come up with a better result. But first of all, let's just see what the default parameters are. All right, cool. So let's look at n-estimators. So the default is 100, and the learning rate default is, where's learning rate? I can't see it. So the learning rate is none. Cool. So gradient boosting works better if we have more estimators and a low learning rate. So let's do a higher number of estimators. Let's see, let's do double. So let's do 200, for example, and let's do our learning rate of 0.1. Let's try that and see if we can come up with a better result. Cool. So our new result is 17,406 compared to our previous one, which is 17,662. So our model did perform better, which is good. Step number 3, we want to break the model. In this step, you will create a model that performs worse than the original model in step 1. This will help you to develop your intuition for how to set parameters. You might even find that you accidentally get better performance, which is ultimately a nice problem to have and a valuable learning experience. So this time around, we are going a different direction. So this time we're trying to get a result that's worse than model number 1. So we're just repeating the whole process here. So we're fitting to our training set. And then we're predicting. So my model 3.predict, we want to pass in x valid and calculate the mean absolute error between predictions 3 as well as y valid. We want to uncomment. All right, so we want to get a worse prediction. Cool, so let me just copy that because I'm too lazy to type. All right, let's think about how we can make this model worse than model number 1. X train, X valid, Y valid. Okay, cool. So here we can see that we get a lower, a bigger mean absolute error than model number 1, which is, which one is our, so our first model returned 17,000. Whereas this one returned 127,000, so which is way bigger. And the reason for this is because we set n estimator equal to 1, which is underfitting the model. We're only using one naive model as our XGBoost. Just remember, when you're doing XGBoost, we want to have ideally a high number of estimators and a low learning rate. Cool. I hope that is helpful. Let's now move on to our final lesson for week number 2, called data leakage. All right, so in this tutorial, we will learn what data leakage is and how to prevent it. Leakage happens when your training data contains information about the target, but similar data will not be available when your model is used for prediction. And there are 2 types of leakage. One is called the target leakage, and the other is called a train test contamination. So let's look at the first type of leakage first, called the target leakage. So target leakage occurs when your predictions include data that will not be available at the time when you're making predictions. Cool. So here we're given an example. Imagine that you want to predict who will get sick with pneumonia. And so the main idea here is that we're trying to come up with a model that will be able to predict who will get sick with pneumonia. So I'm guessing this first column here will form our target variable. We want to come up with a model and build a model that will be able to predict either true or false for this particular column. And I'm guessing the other columns here would form our features or our predictor variables. And you can read all this in your own time. I briefly had a scan through this before I started filming. So I think what they're trying to say is this particular column here, called took antibiotic medicine, is directly related to our target variable in such a way that when a person is diagnosed with pneumonia, that will inform them as to whether or not they should take antibiotic medicine. So this information will come first, followed by the information in this column. So when we're building our model, we shouldn't include this particular column into our training data. So this is essentially an example of what we call a target leakage. That is, we're feeding our model with data that it should not have because the information in this particular column should only be available after we get information about this. Whereas these information below, these ones we can collect before we make predictions, right? For example, we can collect information about a patient's age, a patient's weight, a patient's gender, all before we make predictions. Whereas with this one, we have to wait until the values actually get determined in this column before we know what the values for this column is. I hope that makes sense. So this is a good sort of diagram of what is happening. Let's now move on to train test contamination. So essentially what this is we are sort of exposing the data in our training set, in our testing set. So our models sort of have a preconceived idea of what to predict already. So the reason why this is bad is because our models sort of have a preconceived idea of what to predict in the test set if we sort of contaminate information from the training set to our test set. So in that particular scenario, if we accidentally cross-contaminate between the two data sets, and so therefore if we're not careful and if we're not aware of this, the model will perform good, but when it comes to actually predicting unseen data, the model will perform very poorly. So I think just to bring your attention to this final paragraph here, if your validation is based on a simple train test split, exclude the validation data from any type of fitting, including the fitting of pre-processing steps. This is easier if you use scikit-learn pipelines. When using cross-validation, it's even more critical that you do your pre-processing inside the pipeline. Yes, so this one sort of addresses the lesson that we looked at in the previous video, which is building pipelines and how important pipeline is in being able to sort of separate the pre-processing steps. The danger with doing train test split is sometimes we tend to forget that when we're doing pre-processing on the training data, we're using the sort of the same information in the testing data, and that sort of contaminates our testing set, which is meant to be completely separate and completely independent from our training data. So pipeline is for you to sort of chain pre-processing steps as well as the modeling step in one single step. Because those steps exist within a pipeline, we can be rest assured that the training set and testing set are completely different. They don't mix, they don't match, they don't cross-contaminate, which is exactly what we want. Cool. So with that said, let's now move on to the example. We're going to look at some examples of target leakage. In this example, you will learn one way to detect and remove target leakage. Cool. So this is the data set that we're working with. We have 1,319 rows. Since this is a small data set, we can use cross-validation to ensure accurate measures of model quality. Cool. So just to revise on the pipeline lesson that we looked at a couple lessons before. So we have a pipeline here, we have a random forest classifier because this is a classification problem. And we also have a metric for model selection called cross-validation score. Cool, so our pipeline consists of our random forest classifier, and then we want to do 5-fold cross-validation, and then we want to return the mean of those 5-fold cross-validation. So the cross-validation is 98%. With experience, you'll find it's very rare to find models that are accurate to 98% of the time. So let's look at this more clearly and see if there's a reason behind this spectacular, almost perfect model prediction. So here are the different features in the model. A few variables look suspicious. So for example, does expenditure mean expenditure on this card or on cards that are used before applying for this particular card? So if we do some analyses, we can see that fractions of those who did not receive a card had no expenditures. So those that don't have a card just yet don't have expenditures. So that probably indicates that the expenditure is tied to this particular card. And so this goes back to the previous example that we looked at with pneumonia. So this particular feature will only be available to us once that person has the card. But what we want is the data that comes before the card becomes available. So what we should do is that we should exclude and drop that particular column from our training data. It's not surprising that our model appeared to have a high accuracy, but this also seems to be a case of target leakage, where expenditures probably means expenditures on the card that they applied for. So we probably want to exclude that. Since share is partially determined by expenditure, so we probably want to drop these two features. The variables active and major cards are a little less clear, but from the description, they sound concerning. In most situations, it's better be safe than sorry. If you can't track down the people who created data to find more, you are better off just like dropping the data that you're unsure of, which is very good advice when it comes to the real world. Like if you're not sure, just better be safe than sorry, just drop it altogether. Cool, so essentially we are dropping these 4 features from our data. from our features. And then we want to rerun our pipeline and recalculate the cross-validation score. So as you can see here, our cross-validation score has come down to 84%. Which is a bit lower. So in conclusion, data leakage can be a multi-million-dollar mistake in many data science applications. Careful separation of training and validation data can prevent train test contamination. Pipelines can also be help to implement this separation. Likewise, a combination of caution, common sense, and data exploration can help identify target leakage. Cool, so let's go ahead and set up our exercise. And while that is loading, let's look at step number 1. The data science of shoelaces. So Nike has hired you as a data science consultant to help them save money on shoe materials. Blah, blah, blah. You can read all this in your own time. Do you think the leather use feature constitutes a source of data leakage? If your answer is it depends, what does it depend on? Cool. So we want to predict how many shoelaces they will need each month. The amount of leather they ended up using in the current month. So I think it is an example of target leakage because when you're producing a shoe, leather will be probably one of the materials that you probably need to consider when you're producing a shoe. And so therefore, if we pass in that particular information into our model will be able to recognize that, okay, so if we have a higher amount of leather, we would have more shoes, we would have produced more shoes, and we would have needed more shoelaces to go with those shoes. And so therefore, that is an example of target leakage. So ideally, we don't want to include that column in our training data, but let's just have a look at the answer to see if I'm correct or not. So the answer says this is tricky, and it depends on the details of how the data is collected. Would you, at the beginning of each month, decide how much leather will be used at that month? If so, that is okay. But if it is determined during the month, you would not have access to it when you're making prediction. Cool, so let's look at step number 2, some more questions. You have a new idea. You could use the amount of leather Nike ordered leading up to a given month as a predictor in your shoelace model. Does this change your answer about the leakage? Yes. So I think if you use the amount at the beginning of that month, we would have that information prior to making a prediction. And so that would not constitute the issue of target leakage. In this particular scenario, I think it is okay. This could be fine, but it depends on whether they order shoelaces first or leather first. So essentially the idea here is that we want the leather information to come before the shoelace information and not the other way around. If it's the other way around, then it's a big no-no. All right, let's look at number 3, getting rich with cryptocurrencies. All right, cool. So here we have a new scenario, a new story. So here your friend has built a model that is able to predict the price of a cryptocurrency. And these are the features that he or she is feeding into that model. So the current price of the currency, amount of currency sold in the last 24 hours, the change in currency price in the last 24 hours, change in currency price in the last hour, number of tweets in the last 24 hours that mention that particular currency. The value of the currency in dollars has fluctuated up and down by over $100 in the last year, and yet his model's average error is less than $1. He says this is a proof that his model is accurate, and you should invest with him. Is he right? And if there is a problem with his model. Cool. So let's look at the features that he's feeding into the model and see if we can find any dodgy features that shouldn't be in there that might have given him the edge in terms of the accuracy. I personally don't see any issues at this point. Maybe I'm just stupid. I'm just gonna run the cell and look for the answer. There's no sort of leakage here. These features should be available at the moment when you want to make a prediction, and they're unlikely to be changed in the training data after the prediction target is determined. But the way he describes accuracy could be misleading. A better prediction target would be the change in price over the next day rather than the sale price the following day. All right, let's look at step 4, preventing infections. We have another example here. An agency that provides healthcare wants to predict which patients from a rare surgery are at risk of infection, so you can alert the nurses to be more careful when following up with those patients. You want to build a model Each row in the modeling dataset will be a single patient who received the surgery, and the prediction target will be whether or not they got an infection. Some surgeons may do the procedure in a manner that raises or lowers the risk of infection, but how can you best incorporate the surgeon information into the model? You have a clever idea. Take all surgeries by each surgeon and calculate the infection rate among those surgeons. For each patient in the data, find out who the surgeon was and plug in that surgeon's average infection rate as a feature. Does this pose any target leakage issues? Does it pose any train test contamination issues? You know what, let's just run the cell because I really don't know. This poses a risk of both target leakage and train test contamination. You have a target leakage if a given patient's outcome contributes to the infection rate for his surgeon, which is then plugged back into the prediction model. Blah, blah, blah. You also have a train test contamination problem if you calculate this using all surgeries a surgeon performed, including those from the test set. The result would be that your model could look very accurate on the test set, even if it would not generalize well to new patients after the model is deployed. Yeah, so I think this text pretty much explains it quite well. So my answer is wrong, but yeah, have a read through the explanation. You probably can get a sense of why those issues exist. Cool. Step number 5, house prices. You will build a model to predict housing prices. The model will be deployed on an ongoing basis to predict the price of a new house when a description is added to a website. Here are 4 features that could be used as predictors. Cool. So feature number 1 is the size of the house. Feature number 2, average sale prices of homes in the same neighborhood. Feature number 3 is latitude and longitude, which is the coordinate. And finally, feature number 4, which is whether the house has a basement. You have historic data to train and validate the model. Which of the features is most likely to be a source of leakage? I think the one that stands out to me the most is the sales prices. We're using sale price as a feature to predict sale price. So I'm guessing it's feature number 2, but let's have a look at their explanation. Yeah, you can go through all this in your own time, but my guess is that yeah, we're using the sale price to predict the sale price. It's that's probably not good. All right, cool. So that brings us to the end. So in conclusion, leakage is a hard and subtle issue. You should be proud if you managed to pick up on this issue in the examples that we just looked at. Cool, so that pretty much wraps up our intermediate ML course, as well as our 2-week course for the 30 Days of ML Challenge by Kaggle. So after this, what we're going to do is we are going to apply the skills and the knowledge that we've learned from the past 2 weeks and work on the project in the competition. To be very honest, I haven't started on the competition and I'm already a week late, and I'm not sure about if I have the time and the energy to do it because I still have work and whatnot, but I'll try my best. In the event I don't have the time or the energy to complete the project, I'll still potentially film a video just to encapsulate and summarize what I managed to do in the time that is available to me. But if you enjoy this series so far, please subscribe to my channel, drop a like on this video. It means a lot to me, and I hope you're yeah, excited about the competition. I hope you've started and making good progress. But until then, until my next video, please take care. I hope you're having fun, and yeah, happy learning, keep learning, take care, and I'll see you in my next video. Bye.